Okay, are we good, Hisham?
I think you're good, Alan.
Okay, all right. Well, good afternoon, ladies and gentlemen. This afternoon, we are going to be talking about in situ load testing and the legal requirements and practicalities. I'm joined by my colleague, Thomas Wynant, and he's going to take the first part of the presentation in which we talk to you about all the legal changes that there have been. It's both exciting and it carries a lot of problems for a whole series of people. So what we are going to be doing is to have a look at the requirements that have occurred because of the latest legal changes. We're going to talk about the lessons of history, and we're going to talk about exactly how we have managed to find a way through in that, and we'll look at that. My screen is frozen at the moment, so I am going to there we go. I've got it now, and that should mean that no, I'm going to hand over to my colleague Tom Wynant to take the first part of this. So if I stop sharing now, Tom,
Very good. And
if you
I'll,
would like to share your screen.
yes, I will.
And by the way, ladies and gentlemen, Tom is the CEO of Stram Group. So
So
over to
yes,
you, Tom.
thank you, Doctor. And I'll put this on the normal slideshow um, setting. But just a quick introduction of myself. I am Tom Wynant, and I'm the president of Stram Group. And we provide technology for assessing structures to be used by engineers to verify structural integrity and to understand how structures perform. Stram was started back in 2008 between Alan Geary, my colleague here, and Dr. Charlie Thornton. And Thornton Tomasetti has built a bunch of tall buildings around the world. And he wanted to make sure that A, they were built right, and B, that if they were degrading, we understood them. So that's what we've been doing. But this came on the heels of Dr. Geary's work, and it was a storied career. He started off in the UK, working for the Central Electricity Research Laboratory, and they did a series of tests where they dynamically shook structures to resonance. And this is an important understanding to have, because you have to understand how structures behave. And to do it under very controlled settings is the only way to really do it. In the US, a gentleman named Ron Mays had a $500,000 contract with the National Institute of Science and Testing, and NIST, Standards and Testing, sorry, and National Science Foundation. So he got $500,000 to shake a building at resonance and to basically take it outside its elastic limit and understand these mechanisms. That was done in the 70s. Alan did 40 of those buildings. So that database of structures propelled other people around the country to test structures. And now the methods that were developed from the 70s and 80s are in the ASE 7, and they're in the codes as we speak. So these are the methods that we're going to talk about, but they came from a long history of research that was basically done globally all around the planet and shared. So anyway, that's the pretext of what we're about to speak here. So the contents of this are the legal requirements for assessing structural integrity. Structural integrity being the operative word that has just entered our discussion around the country, but it's always been in ASCE 7. Review of the collapse of buildings in the US, which just recently happened. Lessons from collapses worldwide. The legal framework, changes to the legal framework, structural integrity definition, in situ load testing, and the use of in situ load testing for forensic investigations, and the recent experience of structural investigations. So we've got a lot of slides to cover, and I'm going to try to move quickly through the first 20 to give it to Dr. Giri, and hopefully we can get through them all, because there's a lot here with examples at the end. So I hope you all tune in. So some of the new buildings that have big problems. These are two that you're all probably familiar with. 432 Park is a building in New York City, and it was not commissioned. All of these buildings, if they had a load test, we'd understand how they perform dynamically, but it has some major structural problems that led to flooding on 8 floors. So this is the type of reason why doing this sort of commissioning and this load test when a building is first built makes a lot of sense. It's part of a big lawsuit now, and it's going to be very expensive for the engineer, for everybody. And the Millennium Tower here is well known. It had a foundation problem. There was a $500 settlement on it, and it's in a liquefaction zone. So it's tilting right now. There's cracking associated with it. And without getting into, we're not part of that investigation team, but I think everybody's familiar with it. And the reasons why you want to commission structures to begin with, even new ones. But looking at some of the older ones that have really driven what precipitated these recent legal changes. And the Champlain Tower, I'm sure you're all familiar with, a tragedy, 98 people died. It was $1 billion loss for the insurers. 13 different companies had to pay into that. It was 40 years old, which isn't extremely old. It was right on the beach. Damage increased exponentially. And that's really the point about the degradation of structures that we're trying to make here. So it had some deficiencies with rebar and waterproofing, but by 2018, it had an estimated $6 million in damage, potential damage to be repaired. And then just 2 years later, that went up to 15 million. It speaks to the exponential nature of damage. And then after the collapse, the repairs were about to start. The pool disappeared, and we're waiting for a report. But the point of this is, and we had conversations with some of the code committees afterwards, how would you have known that there's an issue? And to be fair, it looks like this was a podium level failure. And there was a punching shear created from a podium level failure that possibly pulled out the bottom of that building. But yes, you can measure segments of the building, portions of the building, or the building itself. Understanding its risk is the first step. But right now, we're not doing this. And for this building, I think we could have helped with that. And these methods are definitely going to be able to help with understanding risk and mitigating it. Another recent failure, 100-year-old building in Iowa, 3 people died, 1 woman lost both legs, tragedy. Everybody is homeless now who lived in that building. New York City has 200,000 to 300,000 5-story walk-ups that are similar to this, certainly in design, maybe not as big, but they have them all over the place. This one had significant deterioration. It was bought in 2019. Had failing bricks. They painted it to make it look better. Well, isn't that familiar? That doesn't fix it. It just paints it. So we're hiding problems. We're not understanding them. They had a wind event in 2020 in Iowa. Very strange, right? So they had a Direccio and had maximum winds of 126 miles an hour, 70 miles an hour on average for a whole hour. So it was weak to begin with, and then it started showing real signs of damage. So this is a wake-up call in that when you have a structure that's compromised, whether it's in Iowa or down in Florida, if you're seeing signs of damage, you can measure this and then you can track it. Right now, we're guessing as a society, and that's not a good idea. So now we have a change in law. Structural integrity became the operative words. So what that definition is, Dr. Giri is going to go into, but it includes lateral capacity and making sure it's tied together. Understanding what that capacity is and verifying the mode shapes gives an understanding of this. These techniques have been used in the codes. This is chapter 1. Chapter 1, structural integrity is right in chapter 1. It's a need to know in ASCE 7. So the codes allow for testing of structures, and Dr. Jury's, well, we're going to touch on that. And you can't really verify structural integrity without a measurement. Most buildings have all of the structural elements covered. So now an engineer's got to walk through that. He's got to stamp a letter, or your report that says, I have verified this and it has structural integrity. And that is a big leap from doing a visual inspection. And the fact that the law has now focused on this in multiple states and federally, it is a change in the standard of care. So the Florida law was the original version of this. Vertical elements of lateral force resisting system have suffered damage such that the lateral load carrying capacity of any story in any horizontal direction has been reduced by more than 33%. So this is a quantification of how much damage is allowable. And so now, don't you need to measure it? The capacity of any vertical component, 20% from its preceding pre-damaged condition. So we have these metrics here that give you an idea of why you need to measure them. So they give a definition of substantial damage, a condition with one or both of the following. Vertical elements of the lateral force resisting system have suffered damage such that the lateral load carrying capacity in any story in any horizontal direction has been reduced by 33%, and the capacity in any vertical component going back to 20%. Its pre-damage condition and remaining capacity of such affected elements will respect to all dead loads and live loads is less than 75% of that required by the code. So we have performance metrics here, and performance metrics are not uncommon, and that's exactly what we need to understand, is that there's a way to measure performance. So a year of legal changes. 2022 has looked for the verification of structural integrity. The Florida law is actually Senate Bill 154 is what was signed on the 13th of June. The New Jersey has a Senate bill in 2760. Jersey City passed an ordinance. Westchester County was working on language. And this is really an important one that Freddie Mac and Fannie Mae had put guidelines in referencing structural integrity. So it's in chapter 1 in the code. It's now in these different states and their legal definition. And now it's done on a federal level. It really is a national issue. So Senate Bill 154, signed June 13th, provides for inspection guidelines and end implementation. They did a study trying to support how do we implement this. And they talked about non-destructive testing. The draft report, in that draft report, it does reference the method that we're talking about here as a way to do a load test on a structure to verify structural integrity. So it's now kind of in the process. They also have reserves for repairs, and that's a really important thing. Now, people have money to pay for things like testing and repairs. Over the last 40 years, as they were evolving this, a lot of the community boards could opt out of putting money into reserve. And now they didn't have money to fix things and they made bad decisions. So they're dealing with a game of catch up there. And they're seeing that there's exponential degradation. So the other thing is transparency of information. So now an engineer has got to make an assessment of a structure and everybody's going to see it. And he's got to stamp that this thing has capacity. And those requirements are inspection of load-bearing elements, walls, and primary structural members and primary structural systems. Well, if it's covered up, you can't inspect that. Then, to the extent reasonably possible, determine the general structural condition of the building as it affects safety of such building. So what's reasonably possible to meet this intent? These are items number 1 and 2 in the law. as it comes to the inspection process. So we need to understand the structural system, and this puts the onus right on the engineer and the responsibility on the owner to have this done effectively. So they really do need to take this seriously. So the legislature finds, is about structural integrity. The legislature finds that maintaining the structural integrity of the building throughout the life of the building, its service life, is of paramount importance in order to ensure that buildings are structurally sound so as to not pose a threat to the public health, safety, and welfare. And then they have a statewide inspection program, and this is for condominiums 3 stories and above. But they've defined the terms, they've defined the standards, they've also defined this, the documents and codes and standards to use. So it's pretty much defined, and again, it's a change in the standard of care. A structural inspection of a building, including inspection of load-bearing elements, walls, and primary structural members and primary structural system, and to the extent reasonably possible, determining the general structural integrity. Sorry about that. And then after the primary inspection, there's a phase 2 inspection. And that phase 2 inspection means if something is unsatisfactory, if you have visible damage, then you have to go to a deeper dive. And this is why they started really honing in on the non-structural testing, or I'm sorry, non-destructive testing, because you got to quantify how things are degrading and you got to quantify performance. So what is substantial structural deterioration? Substantial structural distress or substantial structural weakness that negatively affects a building's general structural condition and integrity. So negatively affects the general structural condition and integrity. In the lens from which we use, if you can measure it accurately, you understand how the building's performing. If you know what the code suspects, then you know what it should be doing. And if you can track its degradation, you'll meet the intent of this. So this can all be done in a day. It does not include surface imperfections such as cracks, distortions, sagging, deflections, misalignment, leaks. So understanding structural distress can be done much more effectively with objective measurements than trying to assess it when a majority of it is covered up. And that includes the exterior. Most of them are stucco buildings. The concrete is covered with a thick layer of either paint or a stucco. So to be able to assess these effectively is important. The inspection, the phase 2 inspection report indicate the manner and type of inspection, forming the basis for the inspection report. Right now, it's mostly visual. Identify any substantial structural deterioration within a reasonable professional probability based on the scope of the inspection, describe the extent of such deterioration, and identify any recommended repairs. State whether unsafe or dangerous conditions, as those terms are defined in the Florida Building Code, were observed. So this is an interesting one. If you can't see it, doesn't mean it's not there. So what's a reasonable thing to do? And you can't put disclaimers that I couldn't see it, so it wasn't there. You're now responsible for verifying the structural function, the shear walls, and the structural connections of this. And they could be in distress and you wouldn't know it. So there's an inherent risk to the engineering community with this. Recommend any remedial or preventative repairs for any items that are damaged but are not substantial structural deterioration. Identify and describe items requiring further inspection. So there's a series of things to do, and load testing, it actually gives you quite a lot of clearance to say that we've done everything reasonably possible. Changes to the Florida bill required before the end of 2024. And Alan, at which point did you want to jump in?
After the next slide, Tom.
Okay, yeah. So changes to the Florida bill required before the end of 2024. So now we have a deadline. The building safety law by the end of 2024 must include inspection criteria and testing protocols. So they're moving this forward. There's a working group in Florida to establish these methods. They issued a report on it. And the standard that has been used is ASCE 1199, which Dr. Jerry is going to talk about. And it gives a lot of the non-destructive testing that's available. And ASCE 11 is going to be modified soon. But anyway, so there's quite a lot of information and progress with this bill. It's signed into law. It defines what structural integrity is. It gives implementation methods. And again, I believe it applies nationwide. So this is an interesting cartoon. I just got it when I was giving a presentation in New York City. And every engineer probably feels this way a little bit, that, you know, he's not smiling very much because he knows what he signed up for as a civil engineer. The contractor wants to pin it on him, but if he shoots them, they all go down. So it just talks about the, you know, the unhealthy nature of not working together or how it can turn destructive. What we do as a company, we give objective information so that everybody has the same information. So you can't say, hey, engineer, this is your fault because you blew the design. And the contractor can't say, I didn't do anything, because you're measuring it in real time with continuous monitoring on construction sites. But I just think that this is a tremendously apropos slide to represent a dysfunctional relationship that can be bettered by adding technology to help bridge the gap. So with that, Alan, I'll let you take over.
Yep, stop sharing then, Tom.
Okay.
Thank you. And I will share my screen and we will go back to that same slide. And I'll take it from there. I think. Yeah. Okay, so Tom has talked about a number of things in the definitions, particularly in that new Florida Code of Practice. Now, it's interesting to have a look at that and see what the exact legal state is, because they've been tinkering with their laws. As Tom pointed out, 2 years ago, they had a law which called up ASCE 7 as a standard which supported what they were saying. And it does. It's a good document. What they did have, what they found after the Champlain collapse, was that it didn't cover the sorts of things that had led to the collapse. And now we're actually finding that we've got a number of other things which are going on. So it was necessary for them to define what they were going to do, how often a structure could be inspected, how it was going to be inspected, and what the items were that a surveyor, an inspector, would actually be looking at. And we really want to bring to you the fact that structural integrity has become incredibly important, because you are now required to assess structural integrity. And how do you do that? Well, I'll be talking to you about some details, but the first thing is define it. What is structural integrity? And it's defined right at the very beginning of the latest version of ASCE 7, which is 722. And they have a section called General Structural Integrity, in which they define structural integrity as all structures shall be provided with a continuous load path in accordance with the requirements of previous section and have a complete lateral force resisting system with adequate strength to resist the forces indicated in section 1.4.2, and that they'll be connected, in other words, to take the load down to the ground. And then they talk in a little bit more detail. You can read the detail at your leisure there. Now, the important thing about structural integrity, though, is that it's been around for a long time. It's been called different names at times. In fact, way back in the United Kingdom, it was called structural adequacy. Why? Well, because of a collapse that there was in the UK, Ronan Point. And I'll be talking in some detail about that, not just because it's an interesting subject, but because it is quoted in the International Building Code in the US, used in the US right now. It's right up there at the front of ASC 7, and it provides details. So essentially, it's the ability of an entire structure and its elements to carry imposed loads without distress. Now, there's something that we have to bear in mind as well. What is distress? And then it becomes a little bit more complex. So on the big picture loading, the imposed loads are those expected in the design process. The expected loads are risk-based. Now, I have sat on code committees in Hong Kong, Australia, Brazil, and given information to Japan and the United States about what to expect. The US has adopted a risk-based code of practice these days. So ASC 7 actually tells you what the probability of occurrence of an earthquake, a flood, or a wind is expected to be. And you choose the return period of those events to be able to decide what the forces are to design your structure. That sounds easy, but it's at that point that it starts getting complex. So the next thing is distress is a function of the type of loading. Essentially, there are three types of things that you have to consider. The first one, the very first one, is human comfort. Now, humans are particularly sensitive to vibrations, and they will, or we will respond to a vibration by saying, yes, I can feel it, or yes, I feel uncomfortable, or my goodness, I need to get out of here now. Now, at the stage that a human says, I'm not sitting around here waiting for things to happen, at that very level of vibration intensity is the same level at which just very light occurrences of damage to non-structural parts of the structure starts to occur. You've still got an order of magnitude before people start running away from a structure, before you start getting very light damage in structural parts of the structure. Now, if we're designing and we're in the linear elastic range, and I'll be saying more about the linear elastic range a little bit later. If we are in that area, then we're designing for normal, everyday type behavior. Of course, people might get very upset about the amount of movement that they're feeling, but inside that range, we're dealing with something which is pretty easy to deal with. The third level is collapse avoidance, and that's what the new codes of practice are aiming at. Avoid this. It's what earthquake engineers have been doing for quite a while. Make sure that we've got sufficient spare capacity, ductility in a structure to avoid a collapse or even a partial collapse. Now, we actually have a series of limit states, and they're listed in ASC 722. What it says is that there are different types of failure that caused by aging. There's partial progressive collapse and there's complete destruction. Now, risk category 1, 2, 3, and 4 describes a type of structure. Risk category 2 is residential buildings, for instance. So what we have there, if we look at that column, is that we have an annual probability of that becoming a problem of aging of 3 times 10 to the minus 5, partial collapse 5 times 10 to the minus 6 per year, and complete destruction 7 times 10 to the minus 7. Now, the latest building in Iowa, which had a partial collapse, was 116 years old. We designed for wind to a once in 50-year event. That is 0.02 probability per year of a failure or taking it outside the elastic limit. So partial progressive collapse is much less likely, according to ASC 722, to occur. At least what they're doing there is saying that to the designers that you should bear this in account, take it into account. And that means that you design to avoid this type of problem. We design for wind loading, earthquake loading, and flooding loading as well, to different numbers. But essentially, what we're saying is that defines the forces which we take into account for design. But the probability of failure in these three categories is something that you also must take into account. 5 times 10 to the minus 6. If you compare this with what you would expect, a reasonable probability of failure, if you as a person are going into hospital for an operation, you would expect that your chances of surviving would be better than, or the chances of failure rather, would be better than 1 part in 1 million. That's what the medical profession calls a Six Sigma criterion. So in other words, for these types of failure, we're taking them into account in structural and civil engineering as well. But that does mean that there's a secondary part to the design in which we must not just take the forces, excuse me, which are going to impinge on the structure, but we must look at the unexpected as well and reduce the probability of failure in those cases. I'll be saying more about this when I come back to talk about Ronan Point particularly. Now, in this case, definition of distress, first of all, human perception of vibration. What we have here is a diagram which shows the frequency of the vibration and then the acceleration amplitude on a logarithmic scale. So the dots, this first curve here, represent 1% of the population, and so on, 2, 10, 50, up to 99% of people accepting or feeling that the vibration is occurring. So you can see there's about an order of magnitude between the most sensitive person and the least sensitive person. So in other words, all of these dots are from laboratory experiment. There has been one and only one experiment on people in a high-rise building under well-controlled vibration of the structure, and that was at 2 hertz, which is why this is in red here. It agrees reasonably well with this range under laboratory tests, and it allows us to extrapolate and to use these laboratory tests for our design. You notice that the curve comes down at 2 hertz and rises again at higher frequency. Why? Because our human bodies are particularly adept at 2 hertz. Why? Because that's the frequency of walking for a vast majority of people. So we've got a number of items to put into our design there. We must avoid human perception of vibration as far as is possible, apart from just occasionally when there's a very strong wind. If it only blows once a year, people are going to complain, but not often. We've got to worry as well about floors vibrating. We've got to worry about the sway of buildings, and we've got to worry about the movement in bridges. If you're sitting in a car which is stopped on a bridge, undoubtedly you will feel the motion of the bridge going up and down. It occurs at a very low frequency, but I'm sure most of us have felt that sort of thing occurring. The next is the linear elastic range, and generally speaking, we use that for wind loading. And we use Newton's second law of motion. Force equals mass times acceleration. This is the basis still of all our calculations that go into the design of structures. And since we're on the subject, in situ load tests belong in the same category. Force equals mass times acceleration is what drives it. Sir Isaac Newton, in 1660, the Royal Society was formed amongst a number of people. Newton was one of the early fellows. You cannot just apply to join the Royal Society. You have to be invited. You have to have been right at the very top of your profession to be invited in the very first place. So a small group of people got together, and all of the things that we just assume are normal for us derived from people who were members of the Royal Society right at the very start. The saying, the basic saying of the Royal Society is, don't just take anybody's word for it. You need to verify using the scientific method about what's going on. And in situ load testing applies all these principles. It takes Newton's second law of motion, it takes Young's modulus, takes Hooke's law, and puts it together with a verification which is scientifically okay. So this is what we're talking about. If we look at a stress strain diagram, basically, and we extrapolate it to an entire structure, we have a force and a displacement. It's what stress and strain are, but on a very small amount, on individual elements. So we get an area which we call the linear elastic range, and we have a stiffness associated with that, which shows the ratio between displacement and force. So if we're testing a structure, we measure displacement per unit force. Okay, measuring force has always been a problem, but I'll show you in just a minute how we get around that, and that in fact the displacement per unit force is much easier to assess than the modal force. So we have this area where the stiffness is a constant until damage starts occurring. This is pretty much the limit of wind design, although occasionally we get into some other areas here. And in seismic design, we have beyond the elastic limit and damage occurring in a structure, so that we don't do too much damage. It doesn't fall down, doesn't lose stiffness altogether. So structural integrity. We are interested in both ductility and earthquake response. And it's common practice in earthquake engineering to take this into account. This is a diagram which is used. It's similar to the one I've just shown you, but now this diagram, this is again a displacement and force type of diagram. So we've got a stiffness, an initial stiffness. Again, we have the elastic range here, and post the linear elastic range, we get some sort of damage occurring in a structure. And there is yielding which could occur until we have a fully yielded strength right over here. Now, as we use up some of this, then we find that the K value also changes. So I'll come back to a little bit more detail on that in a moment. What we can do is use Newton's second law to look at the relationship between displacement, force, and the characteristics of the structure, which are damping, frequency, and the mass of the structure. So if we rearrange this equation into this form, we have displacement per unit force. And all we have to measure is what's on the right-hand side of the equation: damping, frequency, and mass of the structure. Well, if we take the structure before an event, like a strong wind or an earthquake, and after, and we take this ratio of x upon f before and after, the mass just drops out. So we don't even have to weigh the building or the bridge or whatever else it is, which means that we can take measurements at low amplitude here and not worry about getting up here. We'll have to take it into account, but we'll do that by any change in the stiffness which occurs. So if we take this ratio before and after, we find risk because we have the measured performance, making measurements over the expected type of response. Now, if we do that, then we have a risk ratio, and the risk ratio itself can be expressed as something like there's the once in 50-year wind, the return period 50 years, 2% chance of occurring per year. And we'll get down to 0.05% because it's a logarithmic curve. Then we find at 1.4, then we get a 0.05. We've got this on a traffic light scheme here at the moment, and that's because we've followed pretty much the New Zealand code in this particular case: 1/3, 2/3. If it's got 2/3 of its expected capacity, then it's in the green zone. If it's got 1/3, pull it down. So we've got these three areas where it's quite okay, or more or less okay, and no, pull it down. So in other words, we've got that, but the question is, does this take us there? This is from my colleague in BRE days in the United Kingdom, showing a 5,000-year history of the Earth's of the Earth, and this is for wind occurrences. Each red dot here is a wind event, which is the design event, the once in 50-year event. So what we have is a number of 50-year events in which we have one once in 50-year event, others where we have two, others where we have three or even four, others where we have none at all. In fact, we can have 150 years there of no 50-year events. Nothing is changing. Nothing is to be expected outside of a normal random event. But we do know that some things are changing at the moment. So this diagram may actually be modified somewhat in the future. So this is how damage starts at the microscale. This is a scanning electron microscope picture of an unstressed concrete sample. Well, in fact, this is showing the cement paste. It's undamaged, and if you have a look, you can see a number of things which are of interest. You see needles, you see an early development of a crack, quite normal. It's when they join up that the problem occurs. So this is a normal SEM picture of concrete paste. Now, what we do is we normally look at stress strain curves, and we look at increasing load, decreasing load. We have localized linear elastic ranges, but as we go creating damage, then this develops. So the green line shows us before damage, the red line shows us after damage. And what we find is that gradually this whole curve bends over. The stiffness of the structure of the element that we're looking at changes, and in fact, the light blue curve down at the bottom here shows you that it's losing energy overall. Losing energy, yes, because the amount of area that there is underneath this curve shows us the energy that's being lost. The energy that's being lost, we actually characterize by a parameter called damping. So we can do that. We can make measurements like that, but there are easier ways to do that. And I'll come back to that with some more information. Now, the aging process, what causes damage in the first place? Well, I want to go back to our scanning electron microscope here. And here we've looked at two samples, this one and one to follow. This one is taken from a low stress area of a building subjected to a typhoon. Typhoon is the East Asian approach to cyclones occurring. It's the same meteorological event, but it's somewhat different. Now, you see in the cement paste, there are different chemicals which form different areas inside the material here. And you can see needle-like elements inside the paste. Taken from a high stress area, we find this. Now remember, it's come from the same building. They took their cement from the same supplier, and they were at slightly different times, but essentially they were the same category of cement which was put in. And since these measurements were made probably 10 years after the building was put up, there's no real difference because of the timing of the of pouring the concrete in the first place. So the needles are broken, and when we actually looked at the chemical constitution of this cement paste, we found enormous differences between the two. So in other words, damage occurs not just because of cracking developing, but also right the way up to small chemical changes within the material. Now, we were particularly interested in concrete at that time in Hong Kong, which is where it happened. We were also interested in steel. And laboratory experiments showed that there are similar changes in steel. Not the same, but similar. That in fact, the loss of stiffness, the change of materials inside the steel were very similar to what occurs in cement. Now, we've got a problem at the moment. Buildings are falling down. We have aging infrastructure inside the United States. How did it start? What was going on? Well, it started with this, Ronan Point in England. This was a 24-story building, and there was a gas explosion up on the 22nd floor. It blew the roof off of that area, It went up, took down the roof above it, and then fell downwards. And it took down the floors. As the loading increased, as a floor and a ceiling fell down on the floor below, it couldn't withstand it, and it kept on going down. So this was called a large panel type of construction. It was based on a Larsen-Nielsen design, which came from Scandinavia. And what this did was to say, we can put these panels together. Now, the integrity of the building depended on each of these individual panels being well connected together. So it was a low-cost type of construction at a time when a lot of construction had to go on quickly. Originally, the Larsen-Nielsen system was only allowed for buildings which were 5 stories or less. The United States decided, we're going to take care of this. We will not build any of these taller than 5 stories. In the United Kingdom, we had this gas explosion. We decided that collapses were not a good idea. The local council repaired the building. They rebuilt it. They put an extra column in this area, which was supposed to add stiffness. Well, it did add stiffness. They say it was strengthened. In 1984, a group from the building research establishment shook that building, vibrated it with a system of vibrators, measurement of the movement of the structure using accelerometers. I was the head of that team. We also looked at the way in which panels were joined together, and we looked at joints throughout the structure. Now, this is important because what we were doing was looking for whether those joints were continuous or whether they were moving. It's the sort of decision that you make when you're designing a structure. Anyway, we went and measured them and found that a high percentage of them were not good. In fact, some of these external facade panels were swinging about. They were connected at the top, but not at the bottom. So anyway, that and a fire test decided the code committee in the UK at that time that the code had to be changed. And particularly, they said, we will not have gas in structures taller than 5 stories. So the problem will go away. We'll also make sure that designers make sure that things are connected well together so that the loads are taken down to the ground, and we will never have a progressive collapse again. Inside the building research establishment, we built a 1/4 scale model of the Ronan Point type of building, and we blew it up. We had gas explosions inside the structure, and this was to the new design. Ostensibly, it was to show that we were not going to have any progressive collapses again. And look what happened. All that we'd done was to show that it just needed a bigger force, and the same mechanism will occur again. As a matter of fact, just after we created one of these explosions, I was walking on the ceiling on the top of this building when a colleague shouted to me, "Get off." So I got off very quickly, and this happened not 30 seconds later. So in other words, what we'd shown was that, yes, it's a good idea to change the codes. It doesn't change the mechanism. It just moves the trigger point a little bit up the scale. Now, the point about this is, I should just say, we changed the laws. But this about the quarter scale model and changing the trigger point are just secrets. Your the UK government didn't want the world knowing about that sort of thing. So what we actually showed was that there were two things going on. First of all, the structure is a system, and secondly, we need to find out what the structure actually behaves like in the real world. We do that by getting feedback. And this system theory diagram shows what happens. First of all, you have an input. For us, it's a force. The system is a structure, and the output is the response. And the goal is safety. We actually want to look at what the structure really does and feed it back into what are those forces going to be. And in practice, if we don't have that, then what we have is an unstable system. So now we are told we need to verify structural integrity. So as Tom has said to you, there's a paradigm shift. 2022, after the Champlain collapse, there were structural integrity laws initiated all over the place. We've been involved with some of that, talking to the people who are talking about changes to laws in Florida. We've talked in New Jersey, and we've talked to other places as well. Freddie Mac and Fannie Mae have added language on structural integrity to their requirements about insurance. ASC 1199 is actually adopted as a standard, and it defines how load tests can be conducted. So in other words, for our system, they're actually talking about the way to get the information that you can feed back. And then there's the IBC and ASC 7, which is developed through 10, 16, 22, and they mention that you should be measuring what's going on. Well, of course, the standard is that we go in and we have a look and see what we think has gone on. But if you look, you'll find that there's everything in the codes and the standards which tell us what to expect. First of all, there is a requirement for a minimum stiffness for both seismic and wind design. How? Well, they tell us what the frequency is expected to be. You'll find that in the International Building Code, and you'll find that in ASC 7. You'll find values of frequency which are most likely to occur. Basically, they say measure the height of a building or the length of the main span of a bridge, and you will actually find what the frequency is likely to be. And of course, the frequency tells you frequency is 1 upon 2 pi root k upon m, where k is the stiffness. So if you know the mass of your structure that you're putting in, the frequency will tell you directly what the stiffness is. Simple. The other item that you need to know about is the energy dissipation. You need to know about whether soft stories are part of the design, how the torsion is managed, damping, the energy dissipation of a structure. That gets quite complex, and it's actually kept apart the earthquake and the wind communities for a very long time. Now, in the last 10 years, we've managed to bring the two together and said, look, a building doesn't actually know whether it's going to be assigned a wind loading or a seismic loading. It's the same building. So it has the same properties to start with. Whatever information you can get from one will apply to the other. It may not apply directly to going up to extremely large amplitudes. Those are different things that you have to take into account. But basically, There are properties on an individual building which you can take into account, and you can expect values for the design that you have. Next is the Bureau of Mines, RI 8507. What they did was produce a number of explosions underground and then make measurements on the buildings, which are various distances away. They looked at the vibration intensity. They looked at the damage was occurred. It was published in 1981. Imagine what things were like then. Imagine what technology was like. Imagine what your mobile phone would have been like. They weren't mobile, they were transportable. That was all. So, in other words, what we had was not a very good technology, but we had an excellent investigation into vibrations in 1981. We still use what came out in RI 8507 all these years later. Nearly half a century later, we are still using the criteria. And there are warnings all the way through 8507 saying this is applicable only in certain circumstances. We only looked at domestic dwellings. We looked at wooden built housing. We looked at various things. You may go outside what we looked at. If you do, then take other criteria. But we don't. We use 8507 for vibration intensity everywhere, all the time. And we do so at our peril. We do have in fact, it's an ASCE committee working on the performance requirements for structures. But there are other committees that are also working on this as well. And there are some performance requirements in other disciplines as well. So, structural performance measurements, though, will actually show that we can meet all the requirements and that we can measure what the response of a structure is. We can treat it as a system. We can look at the displacement characteristics. We can look at the displacement per unit force, and we can thereby actually find out what the real performance and the real risk of a structure is, independent of whether it's new or whether it's old, if it's had aging, if it's been subjected to a number of events through its life. So there we have the in situ load tests are specified. They've been specified for quite a long time. In fact, they're in codes and standards. And they say, all of them say, the building official is authorized to require an engineering analysis or a load test or both of any construction whenever there's a reason to question the safety of the construction for the intended occupancy. So in other words, engineering analysis and load tests can be conducted, and they can be conducted quite easily. So ASC 1199, this is only 25 years ago, it actually specifies acceptable methods of providing load testing. They are analysis and interpretation of data, dynamic load tests, monitoring the dynamic response, monitoring stress against strain, and static load tests. We actually use 3 of those. Now that's the standard 1199, and it does say determining the dynamic response is an approved method. Now, if we actually look at 1199 and we say these are the 5 methods, what we actually find is analysis and interpretation of data, limited by the amount and the type of data recorded, can be very expensive. Dynamic load tests, mainly applicable to system buildings. So in other words, if you've got a system which you're applying to a lot of different buildings, then you apply dynamic loading. Perhaps you have a vibrator system, but that's expensive and requires specially made equipment to apply exciting forces. As a matter of fact, in the UK, at the time of Ronan Point, we actually created a vibrator system. It cost us about £500,000 to build, probably $1 million in today's money. And we required a team of 4 on site for at least a week, anything up to 2 weeks to get the information off. We have gone a long way since those days. It's nearly half a century later. So we can monitor the dynamic response. In 99, they said not very applicable in identifying specific deterioration problems. Well, it's all changed within the last 10 years. You can now measure not only the dynamic parameters, but you can identify areas of a structure which have stiffness weaknesses. And it's cheap as well. It's no longer $1 million to do a test. It's now a few $1,000s. Then you can monitor strain and stress. The thing about that is that what you do is put strain gauges in various different places. How are you going to decide where to put it? Well, you put lots of strain gauges in, and that means it becomes very expensive, and you have to choose the right places, so long as they're accessible to you as well. Static load testing, yeah, it's possible with some structures, bridges, for instance, but it is expensive. Static load testing for buildings, it becomes impractical, really. Now, Tom said to you that by the end of 2024, the Florida new law says that there will be a requirement which will be specified in the new law about how in situ testing methods can be performed. They have 16 of those methods, and this is a list of them. Acoustic emission, in other words, if there is cracking, the cracks when they're working actually give off sound, which is a form of energy. Sounding techniques looks for the same thing. So does ultrasonics. Ground penetrating radar, looking at if something has gone wrong, if there's cracking, or if reinforcing has got a lot of rusting with it. Thermography has a problem because what you do there is look at heat, and if there's cracking which is working, then that gives off heat as well. It's another form of degrading energy. In fact, if somebody has also got an oven working on the other side of an area that you're particularly looking at, then thermography is a non-starter. There's fiber optics. That's fine if at the time of design you put fiber optics inside all the way through, all the cement or inside the steel members. That's possible, but it becomes very, very expensive then. Imagery, you can use photographs to see if there is an excess of moving in some places, and same with AR VR imaging. You compare with what it looked like for a baseline structure, and you compare a movement. Speckle core interferometry is a good way of doing that, but it's not as sensitive as you really need. There is dynamic analysis, and I'm going to show you more about that because I think that's a really good way of getting an in situ load test and doing it cheaply. Integrated sensors, again, you need to place those inside the material or inside the building. How do you do that? You have to decide where you're going to put them to start with. X-rays, again, you have to decide where you're going to go to use your X-ray to find out. Core sampling, well, yes, if you're able to take cores out, you'll find out if there's a bit of a weakness in some places. In situ strength measurement, yes, it's possible. Again, a hammer test will tell you. If again, you have to go to the place where you need to know. Corrosion detection, number of ways of doing that. Ingress and transport, carbonation. Of those, dynamic analysis is the cheapest and quickest. Not only that, it is the only one which will allow you to get the complete response of an entire structure. Everything else in this list says you've actually got to somewhere, to go to somewhere where you think there might be a problem. So in 1989, there was an NSF NIST paper, and that produced 48 recommendations. So we have 34 years later, most of them have materialized, but some didn't. The key recommendations that are still not broadly applied. If you're doing a finite element model of your structure, it needs to be calibrated. If you don't calibrate it, the designer has got an awful lot of guesses to make about how the building holds together. Second one, system identification, damage detection. And the problem with that is that you need to be aware of nonlinear analysis. Third one is measurements for the assessment of performance. We are only just beginning to grapple with that. And the fourth one is sharing of information between countries. Well, at the time that in the UK, we were doing the tests on Ronan Point, we shared our information with lots of different countries, particularly with the United States. We even had one of the first internet connections, government to government, at the time. So now let me look just quickly at collapses worldwide, because they actually provide us with some information about what we need to do and what we need to avoid. So we've got Ronan Point in amongst this lot. We've got the Murrah building, which was a terrorist explosion just outside and caused a progressive collapse. We were particularly interested in the UK about wind on cooling towers. We, of course, had the World Trade Center, which also had progressive collapses in the Twin Towers. But we have other things going on as well. A building falling over in Japan, a building in France, one in India, all progressive collapses here. And the Colossus of Rhodes. The Colossus of Rhodes was something that fell down and felled for 800 years before anybody actually pulled it away. Now, what I'd like to do now is to say, yes, there is some information here about the relationship between static and dynamic responses. And my computer has just frozen up because I pressed the wrong button. Bear
Alan,
with me.
just to let you know, we're at an hour, 15 minutes in, and you got 45 minutes left. So
Yep,
just,
I know. We'll
okay.
stop a little bit early to try to allow people time for questions as well. Okay, Tom. Okay, I'm going to stop the share at the moment and then just come back to that, I hope. Bear with me.
just to kind of summarize what Dr. Jury had said already, was that, these performance measurements that we're talking about evolved since the 70s, 60s and 70s even. There was a lot of testing done by the federal government, universities, and then it was followed up all over the world. One thing you didn't mention is right in ASCE 7, they reference a website called vortexwinds.org. And in that are 1,000 building measurements using these dynamic techniques. So this isn't new. This is something that's evolved over many decades, but the methods that, excuse me, Dr. Jerry's talking about, nonlinear look at damping, nonlinear looking at frequency, and the mechanism of fraction mechanics that underwrites it. So both the fundamental frequency of a structure, that's referenced in ASCE 7, and the superior methods of measuring nonlinear behavior is also referenced. It's all in the commentary, and it gives all the supporting documents. So
Okay, thanks, Tom. I'm go
okay.
again now.
Very good.
Now, what I want to do is to say, okay, how do we do this in situ testing? How do we measure the performance? And I want to emphasize that statics.
You're not sharing, Alan.
Oh, okay. Thank you for that. Okay, here we go. All right. I want to reference the fact that statics and dynamics are just two sides of the same coin. Because if we take those equations, Newton's second law and so on, and we apply them to our system, which is our structure, and we set the frequency to 0, in other words, statics, then what we get is that the response is the force divided by the stiffness. If we set the frequency to resonance, then what we find is that the response is the force divided by the stiffness again, but then we get a dynamic magnification factor. Now that dynamic magnification factor is incredibly important because what we get is a diagram like this on the bottom right. We have frequency along here and we have displacement up here. So at statics, we have no frequency. So we're putting a static load onto a structure. Well, there's no such thing as a static load, of course, because it had to be put there by somebody in the first place. If we raise the frequency to a resonance, then we get an amplification factor. And you can see from this diagram here, this video, that at very low frequency, the structure follows the force. At resonance, you get a much bigger response. And at high frequency, the structure doesn't accept the loading. So in other words, we take these equations, which are just Newton's second law, we put them into this, and we measure the dynamic response because we can extrapolate back all the way down to what we do in design. And of course, what we do in universities is we do laboratory tests in which we look at displacement and we have the force applied divided by stiffness at various different forces, various different sizes. And in fact, we've become so used to them that we expect the whole world to be organized like that. It's not. We can put loads onto a structure, bridges especially. In this particular case, we loaded up a truck and moved it slowly, passing over a bridge to test on whether the structure was okay or not. And we got out of it raw data which show us the stresses induced in the bridge. So that was particularly useful. we showed that you could actually roll that truck over the bridge at a low speed. If you got too fast, then it wasn't the same. But in practice, you could run it just at slow speed and find out what the strain and thereby the stress was in each particular case. Came out very nicely as well. Now, if we go back to this diagram here, what we can say is that we are looking now at the linear elastic range, and we found a way that we can extrapolate through this curve up here. We know what the mechanism is going to be up here in the seismic zone. And if we have this, it doesn't matter if the structure is going to be subjected to wind or to earthquake. What we have is a way of finding out what this initial stiffness is. Statics is a special case of dynamics, but we've got to be aware of the resonances because they're excited. They're always excited by natural actions like wind, wave, earthquake, and traffic as well. So if we go to a structure and we want to do a test which is based on the dynamics of the structure, we can do that so long as we can measure down to a very low amplitude. And we can, because technology has moved on. So we just need to measure that we've got the dynamic magnification factor, and the dynamic magnification factor multiplied by the static response equals the dynamic response. Excuse me. And if we actually say, okay, we are going to look at a building and we are going to test it, we really need something to test against. That can be what's expected in the code, or we can have a look at that structure when it's first put up and compare it later on. And that's known as structural commissioning. And it's a verification that a structure going up actually has the required strength and capacity that the design assumed. And that means that it's designed to resist what's in the standards that back up the codes of practice. And we can do that by measuring 5 parameters of a structure: frequency of resonance, displacement resulting from the force, mass and mass distribution in the structure, damping associated with the resonance, and the deflected form. The deflected form will tell us if there is a structural weakness somewhere. And in fact, we can take those 16 methods that Florida will be considering up until the end of next year, and we can say 2 of them actually perform what you want to do. There is a dynamic analysis and in situ strength measurement, both through the dynamics. So it's already allowed. Why aren't people using it? Because they're not familiar with it. They actually haven't come to the viewpoint as yet that it's cheap, it's quick, and it answers everything that you need to know. It'll happen because it's so obvious. So the systems approach, let me just go back to that for a moment, because I showed you this diagram, what we want and what we've got. So if we actually have analysis, then we have what's known in system theory as a decision-making interface. So we have what we want from the design, and we feed back information and put it into that, and we adjust our codes. We design, we check our design, modify it as a result, and if we don't, system theory, if we don't have feedback, system theory says that the entire system is unconditionally unstable. So we need feedback. How do we do it? We do it like this. We put a measurement onto the roof of a structure, and then we measure down stairwells. We leave a reference accelerometer at the top, and then take others to various different places. So for a 5-story building, it takes us 3 to 6 hours to do that. A first pass, 1 to 2 hours, and we can, the methodology is non-invasive, non-destructive, accurate, and repeatable. The accelerometers are just about the best that there is anywhere in the world, and we've developed our own what we call a structural cardiogram, which also has low noise. Now put these two things together and we can measure down to the wavelength of visible light. Why is that important? Because if we are down here and measuring, we can extrapolate all the way up into another regime that we're interested in. So long as our instrumentation has low enough noise that we are able to measure very small vibrations, then we're able to extrapolate upwards from there. So why do engineers need to perform a baseline? So measure frequency and damping, categorize the building, locate weaknesses, and adjust the methods as needed. So you can also measure for ground motion and amplification. You can measure ground motion to see if there are voids underneath the ground as well. Track performance over time and track settlement as well, because an accelerometer uses gravity as its reference point, which means that if it tilts over sideways, it gives you not only the acceleration signal, but also the tilt signal. So if you use both of those, you can tell if a structure is settling in some way, and you can see slow progression and immediate events occurring. So there, we measure now displacement per unit force simply by using Newton's second law of motion. And we look at what that K value is, the ratio of displacement to force for the entire structure. Now, let us compare what happens in design. We have representation of a structure in computers. We have a matrix approach. We have the finite element approach, finite differences, and we can look at the geometry of the structure. Finite elements have become the most popular these days. And what we actually do is we take this well-known equation. Thank you, Mr. Newton, once again, and we apply it at various different points to a structure. So we have individual element stiffnesses, we have individual masses, and we simply say mass times acceleration plus displacement times stiffness equals the force. We've balanced there. We put all these together and we actually have a matrix equation. So we've got mass, acceleration, stiffness, displacement, and force. And there are matrices which occur as a result. You put those into a computer program and it is easy to find what Y is. That is the displacement at any point in the structure. So once again, we're facing the same sort of thing. Force times a representation of the structure equals the displacement. F divided by stiffness equals displacement. Simple, isn't it? So there are identifications that we can do looking at the dynamic parameters. We can, if we are actually having a model, it is not a digital twin of the structure because the person who's designing has before them a difficulty in deciding, for instance, how the joints are connected together, whether there are some additions to the stiffness and the mass from facade panels, from glass plating, from so-called non-structural elements in the structure. All of them have some sort of effect on the behavior of the structure. So what is needed is that a digital twin can only become a digital twin if it's calibrated, if you make measurements and you feed it back into the model. Now, you can't do that at the design stage, of course. What you do need to know to do is to put the structure up and then check it to make sure that it was the same as was intended. If it's not, there are things that can be done about it. There are ways in which the necessary computer time can be reduced by nodal reduction. And the output isn't stresses, it's actually displacements. These classical models are very detailed, but they can be a very long way wrong as well. They can be 200–300% out. You can also do load testing like this. This is what we did in the building research establishment. And to show that Newton's laws were right, then we did this calculation up on the right. This is the vibrator system, which has contra-rotating masses and produced a ton force at 1 cycle per second. So you had a force which was oscillating in harmonic excitation of a structure. And when we switched it off, then we would find that there was a decay of the vibration of a structure, which allowed us to take measurements of displacement and of damping at various different amplitudes. And we put together something which has now been repeated in Japan, especially, which allows that second unknown parameter to be put into our calculation of risk. Does it work? Well, yes, it does, despite the fact that there are all these non-linearities, and this is a different structure here. We put in different forces. There was difference in frequency at those forces, a difference in the displacement, and the damping changed. But when you put these all back into Newton's second law of motion, you find that the nonlinearities cancel each other out and the mass is a constant. So just in case you were wondering, and it'll be in your notes, a Newton is approximately 0.22 pounds force. So there is now a way not of shaking a building, but of measuring the response of the structure to ambient excitation. And ambient excitation allows us to look at a structure for longer. This is something which has confounded the earthquake engineers for a long time. An earthquake doesn't last long enough for you to use all of the techniques available. What we do now is to say, okay, we can take what's known as a random decrement signature. We don't need stationarity, we don't need long-term data, and we make measurements. And this down here on the right is a Randex signature of a structure. There is damping against the amplitude of response. Every single point is a different amplitude for a single mode of vibration. And what that shows is that there is a value of damping which it will aim at. If you go over a large range of displacements, what you find is that there is a 3-part curve in the damping, a low amplitude plateau, a rise, and a high amplitude plateau. And all of these are defined in peer-reviewed published papers right now. So it is possible. They all depend on, instead of, as we're all used to, viscous damping, there is a test which was done by Tom Wyatt in the United Kingdom, and it said that what you have is a whole series of elements which behave in a stick-slip way. Certainly, up to a certain amplitude, there is no movement. and then they come unstuck, dissipate energy and decrease. When you put a very large number of these together, then what you get is an overall characteristic which looks like that. In other words, it is equivalent viscous damping. So now we have a mechanism for damping, stick slip methods, and we also have codes of practice which rely on being able to use viscous damping. Well, we've got equivalent viscous damping. And if you look at the history of it, then what you find is that that's what they talked about very early on. Damping occurs in various different places. You can have energy dissipating into the ground. You can have damping devices. You have aerodynamic damping devices on the building itself and the frames and non-elastic behavior inside the structure. And with all those, put all of those together, and you have various different ways of looking at damping. So we now have fracture mechanics applicable. We have an energy mechanism, which we know about. Frequency is easy, and we can actually get a measurement. I'm going to press on just a little bit. I'll just take that saying if we look at the response of the structure at low amplitude, then we measure the structure. If we measure at high amplitude, we measure the structure plus the energy dissipation in the ground. So low amplitude is good if we're talking about the structure and we want to know what the performance of the structure is and if there's something changing in the structure itself. So the random decrement signature was originally used for fatigue defect detection and on the shuttle by NASA. We modified that for measurement on structures back in the mid 1980s, and it's now utilized in lots of different countries around the world. And it can be used to detect damage in structures. Every single point on that random decrement signature is actually a representation of a decay of oscillation with an envelope which has zeta, the damping ratio, in it. So we're able to look at that and produce something which will tell us what the damping is at different amplitudes. So we've got this three-part curve. When damage occurs, what happens? If we have large-scale imperfections, we get a rise or some sort of change in that low amplitude plateau. The rise here is dependent on the small scale imperfections, which I've shown you in the scanning electron microscope diagrams. So that rotates, showing that there is damage occurring inside the matrix of the structure. And then at the high amplitude plateau, there is less energy damping available for us. So the value comes down at very high amplitudes. Now, to show that it actually works, take this site in New York City. And what we had in that wall was a very large crack, which was only discovered after a site hut was taken down. We put accelerometers on either side of the crack, and we measured what was going on. And we looked at damping as well. Now, before they repaired that, this was the damping characteristic that we had. So we had a number of excursions in the damping characteristic with a general increase in the value. What this actually tells us when we apply fracture mechanics is that each of these excursions is associated with a crack length. In this case, this particular large crack and the interstory cracks along here. So we've got those, and you can see them appearing in the structure in various places. It appears in the damping characteristic. After the repairs occurred, then we had essentially our three-part curve. We had a lowering at the low amplitudes. We still hadn't got rid of everything in the very large crack, but the peak had disappeared for the other one. And what we have then is a measure, a really good measure, showing that we've actually taken care of the problem. And this occurs quite often. This was another building which was repaired, and after the repairs, we got the three-phase damping characteristic. And that's all from using this equation. X upon F is 1 upon 8 zeta frequency squared and mass. When we use that, then what we find is that we've got a measure of the damping of the displacement per unit force. And in fact, if we take the measurements before and after event, and we do it at the same amplitude, then we've got a risk ratio, which I was talking to you about before. Now, I've got a few examples of in situ testing that we've done. This is the Fulton Street Transit Center in New York City. We tested this structure. They were building the transit area close to this 11-story brick wall along here. They were very worried about it because it's complex and it was old, and they didn't understand what the problem was. So in practice, what we did was take measurements at an early stage when our accelerometers had actually quite a high noise floor. 2 years later, we'd improved that somewhat as repairs had been done, and we found that the two main responses of the structure had separated. They'd both moved upwards in frequency. And we actually calibrated the structure as well. We produced a finite element program, reduced node finite element program, and looked at the response. There was only one way to get a response together, and that said the floors are only 2 inches thick. Well, that was silly. Whoever heard of a 2-inch thick floor? Until you take the structure to pieces and find that the way they'd built them was actually they'd formed these arches, put in soil over the top, and then a wooden floor over the top of that. The structural element was only 2 inches thick, which was a vindication. So we have also, this is West Point, and we made measurements on that. That's looking from the roof back at the bell tower. Excuse me. And these green dots are places where we made measurements. And there's attachment of accelerometers to an area of the structure. And there's a spectrum analysis showing the response. And you can see that now our signal to noise ratio has got even better. It's pushing 10 to the minus 11 here, but you can see a dynamic magnification factor here. And that was a problem in that particular case, because what happened when we looked at the response at the top of the tower itself, a magnification factor of around 10 times. And that 8507 document that I talked to you about before, that the Bureau of Mines had produced and is used and tells you to measure vibration intensity at the ground level or at within 30 inches of it, assumes that the maximum amplification you can get is 4. We had 10 and an occasional value of 12 coming out there as well. So we told them what was going on, and they decided to alter the blasting regime so that the vibrations were not so large. And that was lucky as well, because we said, well, in this case, what you've got is some new cracking, and we told them the place where it was going to be. They had a look and found new cracking, and realized that if they'd gone on with the blasting as it was, they would have had a collapse of the the nave roof of that building. They were grateful. This is 72nd Street, just by 3rd Avenue in New York City, in which there was a subway being built. And this is underneath, in which a new access down through an access tunnel was being built. So there were transfer girders to take the load of the building, instead of directly down into the ground, through the transfer girder, transfer it, and make sure that the building was safe. Well, we monitored on the girders and on the ground and found, in fact, this sort of thing. This is as the load was being transferred, we were able to convert these measurements to whether it was safe or not, assure them that it was okay. But this was the big thing. Did the frequency of the building change? Not very much, by 0.01 cycles per second. But the damping changed enormously. It changed from 1.2% to 0.9%. And the reason for that is that the building was more monolithic. So damping itself became a measure of showing whether a structure is actually in a good shape or not. It helps you understand it. We also had a spectacular win in New Zealand. We're able, with any building, if we've got measurements going on, we transmit it over the internet. So anywhere in the world, we can sit down at a desk and can actually look at what the response of the building is. Now, Wellington knew they had a problem after the Kaikoura earthquake, which was 7.8 magnitude. This is the South Island of New Zealand, and that's where Kaikoura occurred. And Wellington is just over here. The aftershocks, similar to what was going on in Turkey. There were a lot of aftershocks, which gradually got closer and closer to Wellington. Well, Wellington got worried and asked us to take a look at 10 of their buildings. We didn't know it, but there was one amongst them that they were particularly interested in. It was this one. It had been through 3 earthquakes. Kaikoura was a big one. So we made measurements and we monitored an area in which there was a reduction in stiffness. So we looked at what the frequency was, what the damping was, and went back to them and said, you have got a problem here. Not only that, but we can identify where that problem is. It's in this area circled here on this diagram. So they took the facade panels off and they found that there was a broken structural member. Now, before this, 2 engineers had gone in and had a visual inspection. One of them said, oh, it's about 80% of its old capacity, and the other said it's about 30%. 2 engineers, both using the same rationale for working out whether the building was okay. From our measurements, we went to them and said, it is 30%, and it's not in a safe condition. So they had a long discussion about what they were going to do with the building, but in the meantime, they took 400 workers out of that building while they were deciding what to do. We also had a look at this particular structure, a single-story building, and you can use these techniques in situ load testing on this as well. In this particular case, though, the old Kosciuszko Bridge alongside the building represented for us a beautiful opportunity to create an earthquake for ourselves. So what we did was we made an initial measurement on the structure and found that there were certain weaknesses that we didn't like. In particular, the roof of the structure. We found it bouncing, which meant that if a force came into the structure, It will be transmitted throughout the entire structure. In fact, we also found there was a weakness here, and it was caused by a number of different things. So we measured the mode of vibration at 3.22 hertz, which is only 50% of what's normal. That's a red flag. We also looked at the damping ratio and found that. So then the bridge was demolished, and we used that as an excitation mechanism. We had crack gauges in there on the back wall and found that some of them had increased. The engineer said there was no damage. However, when we looked, the frequency changed from 3.22 to 3.15, which means that there was a 2% change in the frequency. That equates to 4% of stiffness lost. But have a look at this. There's before and after. Before is this. After the event, the frequency has gone down, but the shape of the response has got larger. That only happens if damping has increased. So we measured damping using the random decrement. And here we found that the damping value had gone from 0.9% to 1.5%. So 1.5% means there are more elements in the structure that are dissipating energy. When you put those together, then what we found that the risk ratio said, taking it to the end of the elastic limit, there would be a wind, which occurs on average roughly once every 2.3 years. This also told us that the critical wind speed had reduced from a not very good 78 miles per hour to 66 miles per hour.
Alan, you have 5 minutes left. I don't know.
Okay, I am finishing up here now, Tom. And in fact, I'm going to finish by the last two slides here saying, how do we measure that? We look at the mode shapes. So we look at the shapes that we get of the distorted form of a structure. We look at the torsion, and we look at what's going on in that as well. And you can see in this particular case, this building, that the torsional mode is offset. And this one is a combination of torsion and a more complex second order mode of vibration. So why is it valuable? Limit liability. That's the first thing. Tom showed you that that diagram where nobody's a winner, whereas in fact, this is valuable because it's a due diligence step. It saves money and it adds liquidity. It gives you a very early warning of whether you have a weak structure or not. It prioritizes budgets because if you take measurements on a whole series of structures, then you can pick out the really weak ones straight away, and you pick it up at a very early stage, you will find that what you've got is a way in which you can adjust your budgets to fix what is really a problem. So that relies on commissioning. We would like everybody to commission new structures. If you have had something happening and people are not sure whether they can go back into a structure or not, using these techniques, in situ load testing would allow you to make that decision very, very quickly. So what we're doing here is comparing a structure based on risk, taking the same philosophy as we know and love is used in our codes of practice. And we apply fracture mechanics, system theory, and we have an objective mechanism to improve our building stock. So, ladies and gentlemen, thank you very much. My colleague and I will take any questions that you have at the moment. Thank you.
So let's see, there's been a series of things that have come out, questions that came up, and Roberto Sanchez had sent them out mostly. And he asks basically, what can HOAs do? Because there's kind of a gap in this new law in Florida. And it's like, well, what's the end of the life is really kind of the looming question. And that's an important one. I don't think they addressed it clearly through the progress of creating the law. That nobody was really willing to tackle that issue directly. I think they wanted to make some incremental improvements, and they did. They made some great incremental improvements. So anyway, this one test, this ability to do a load test, as Alan said, is right in the codes. But I think it helps the HOAs quite a bit, because right now everyone's struggling with implementing this new law. There's a lot of different levels of liability that get shed to different elements. To the owners and the engineers specifically. Now they got to verify this. So it gives you some idea of how to verify it. And it is, something that can, I think, help the industry a lot to deal with this new law and mitigate risk for the general population. So I don't think Hersham had just sent a note through chat, and it gave some information about the webinar and how to access it. So with that, I think we're done.
Well, thank you very much, ladies and gentlemen. Tom is right in saying that Florida is going through a phase at the moment where they are looking at the possibilities of all these types of tests. What we've done today is shown you that the techniques behind in situ load testing are there. They're available now, but in situ load testing is already allowed by the codes and the standards straight away. Florida's come to terms with that, and it's now looking at the methodologies behind various different types of load test. And hopefully they will decide that it's a very good idea and that they will apply it to all sorts of buildings in Florida. We are hoping that it might be applied in Turkey as well. So the same sort of problem, only raised by an order of magnitude, occurs there as well. So the big point about using these techniques, though, is that if you get in early enough, then very cheaply you can find out what the problem areas are, and you can ameliorate the whole situation. You can avoid the collapse. Whereas, as it is now, everybody sits there thinking that everything is okay until the point that there is a collapse. We want to avoid that sort of thing. We want a safer world. Thank you.